Alright, welcome everyone to section 5.2, the definite integral. So I just want to again apologize for that terrible audio in the last video. I think I have figured out what was causing the crazy noises. So I'm going to attempt to not touch my computer where it was making the noise, I think. Anyways, I was editing it out because I know some of you are probably listening through headphones or whatever, and I did not want to blow your eardrums out. So again, if you need any clarification on anything in that video, please send me an email and I'll be happy to explain. But today, I think we are going to be okay. I'm just going to hopefully not make those crazy sounds. Alright, so we're going to start off with the definition of a definite integral. So, the definite integral, of a function f from a to b is given by, so we write integral like this squiggle here, so it kind of looks like an S. And then from a to b, so we write a down here and b up here. These are what we call bounds or limits of integration. And so then we have the function f of x dx. Okay, so this is read the integral of f with respect to x, similar to our derivative, right? And so what we're going to notice is that our function f of x is bookended by our integral sign and by the dx. Okay, so if we don't have the dx there, this is not proper notation. Alright, and especially if we don't have the f of x there, that's not proper notation either. Okay, so we need all of these parts to have proper notation. And essentially what the integral does is calculate the Riemann sums, which we learned about in our last video, okay, but on the smallest possible rectangle. So remember how we said if we add more rectangles, then we'll get a better approximation. Well, what if we put an infinite number of rectangles in there? Then we would have almost a perfect approximation. Alright, so that's what an integral is doing. Alright, so let's go ahead and look at example 1. So here we're going to estimate this integral using an average of the left-hand sum and the right-hand sum. So we're still going to be estimating these integrals, okay? So, and let's go ahead and use a length of 1. Alright, so our delta x is equal to 1. So that means our n is b minus a. Well, those are the bounds of our integral. So 4 minus 0 over our delta x. And delta x, is 1. So we have 4 intervals. Okay? Alright, so our integral from 0 to 4 of x squared with respect to x is going to be approximated by our, let's do our left-hand sum first. So for the left-hand sum, we start at 0, right? And we go up to n minus 1, so that's 3. And we want f of x sub I times delta x, which is just 1. Alright. So if we're going to go ahead and write all of this out, we have, I'm not going to multiply by 1 because that's redundant, right? So we just have f of x sub 0 plus f of x sub 1 plus f of x sub 2 plus f of x sub 3. If we're starting at x is equal to 0 and we're going up to x is equal to 3, we have f of 0, f of 1, f of 2, and f of 3. Okay, and f, the function, is what's inside, whoa, calm down, what's inside our integral. It's our x squared. So we need 0 squared plus 1 squared plus 2 squared plus 3 squared. Alright, so if we square these out and add them all up, we get 14. Alright, so that's our left-hand sum. Now we're going to look at the right-hand sum. Alright, so we can approximate this by the right-hand sum. So instead of starting at 0, we start at 1. And instead of going up to 3, we go all the way up to n, which is 4. But we still have f of x sub I times 1. Okay, so let's write this out. Now we're starting at x sub 1. Then we have f of x sub 2 plus f of x sub 3, and we go up to f of x sub 4. So again, f of x is x squared, so we have 1 squared plus 2 squared plus 3 squared plus 4 squared. Square all of them and add them all up and we get 30. Alright, so we've already determined that taking an average is the best way to approximate so far, right? So let's go ahead and average the two. So our integral from 0 to 4 of x squared dx is approximately 14 plus 30 divided by 2, which gives us 22. And just for comparison, the actual exact answer is 21.33. So our 22 approximation is pretty good. Alright, let's go ahead and jump into example 2. So we need to estimate the integral from 0 to 24 of g of x with respect to x based on the following table of values. Alright, so here we don't know what the function is, but we know the function values. Okay? So it looks like our delta x is the space between each step of x, right? It looks like we're increasing by 3 each time. So delta x is equal to 3. And we're going from 0 to 24. So our number of intervals is 24 minus 0 divided by 3. Alright, so that's going to give us 8 intervals. So we need to do our left hand, right hand sum, and then we need to average them to get our best approximation so far. Alright, so let's do the left hand sum. So we have from I is equal to 0 up to n minus 1. N is 8, so we're going up to 7 of g x sub I times delta x, which is 3. Alright, so we need g of x sub 0 times 3 plus g of x sub 1 times 3 plus, and we keep going, until we get to g of x sub 7 times 3. All right. Now, I think you can handle this by now, so I'm going to leave you to check my work here. But I will tell you that this should come out to be 216. That's our left-hand approximation. Okay? So there's some steps in here. And then if we look at our right-hand sum, we're starting at 1, right? And we're going all the way up to n, which is 8. But the function inside is still the same. It's still g of x sub I times 3. So now we're starting at g of x sub 1 times 3 plus g of x sub 2 times 3. And we're going to keep going until we get to g of x sub 8 times 3. All right, same thing just for the consideration of time. All right. If you have any questions on the intermediate steps, please send me an email. But for time, we're just going to go ahead and say that this is equal to 324. So if we want to average this and get the best approximation, we're going to say that our integral from 0 to 24 of g of x dx is approximately 324 plus 216 divided by 2, which gives us 270. All right, so we had one example using the given function. This example, we were given a table of values. And our next example, we are given a graph. I apologize for my little hand-drawn graph over here, but it's the best I got for the moment. All right, so the method we're going to use is simply counting the boxes. All right, so we're going to try to estimate the area. So estimate the area under the curve by counting the number of boxes. All right, so that's exactly what we're going to do for every box under this red line, our f of x function, up to 6. So we're stopping at x is equal to 6, but we're going all the way up to x is equal to 0. All right. So let's see what we got here. I'm going to count all of the whole boxes first. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 11, 12, 13. We'll go ahead and say this one looks whole enough, so we have 14. And let's see here. Maybe 15, 16. And these two pieces together look like maybe half of a box. So 16 and a half boxes. About. It's a rough estimate, right? All right, so about 16 and a half boxes. Well, we need to know the area of each box. Area of each box, if they were drawn to scale perfectly. Well, that's our length times our width. Let's see, I've got so many colors going on. Let's use purple. Our length times our, in this case, our height. All right, so we have 1 times 5 gives us 5. So our total area then, total area under the curve is approximately are 16 boxes, 16 and a half boxes, times their area. All right, so times 5, which gives us 82.5, roughly. All right? So for example 4, pull it up here, we're going to use a calculator to find the following values. So now I'm actually going to switch to a different view, and bear with my iPhone quality camera, all right? And we're going to look at how to use a TI-83. All right, so welcome to a little bit of behind the scenes where I've jerry-rigged my phone so that we can learn how to use a graphing calculator finally. All right, so this is my dinosaur of a graphing calculator. It was actually my mom's when she was in high school, I believe. Anyways, we're going to go ahead and turn it on. Please ignore my crazy nail polish. And the first thing we're going to do is go to this y equals. This is going to be where we have functions listed. Okay? If you have anything there, go ahead and hit clear, just so we get to start with a nice clean slate. And we're going to go ahead and type in, this is the first problem we're dealing with. We're going to go ahead and type in the function, so what is inside our integral here. All right, so we have 2 times x to the 5th, so we do this caret 5, okay? That's 2 times x to the 5th minus 6x, and then we have a little shortcut button over here that just squares everything, okay? And we can go ahead and go to the zoom, and if you hit 6 or just scroll down to number 6 here, you get Z standard, and that's going to be your negative 10 to 10 window. You can go ahead and hit either the button 6 or the button for enter, and we are going to get a graph of our function. All right, so we would like to calculate the integral between 0 and 3. There are our bounds. So what we're going to do is hit the second button, and up here it says calc in yellow. Alright, so after you hit second and then calc, which is the trace button, we're going to get a whole bunch of options here. We want option number 7. So again, we can either scroll all the way down to 7, or you can just hit the number 7, and this is our integral function. Alright, so go ahead and hit enter. And it's going to ask us first for the lower limit. That's our lower bound. Alright, so we're going to go ahead and type in 0 and hit enter. And now it's asking us for our upper limit. So we want our upper limit to be 3. Alright, so we're going to go ahead and type in 3, hit enter, and we're going to watch it shade in the area under the curve, or between the curve and the x is equal to 0 line. You see we get a little bit of area under the curve down here too. And we get our answer is equal to 189. The numeric answer is written down there. Alright, so 189, there we go. Let's do it with b as well. Alright, so we're going to go back to our y equals. I'm going to go ahead and keep this one here, but I'm going to scroll over so that I'm highlighted the equal sign and hit enter. That's basically going to decommission that equation for now, and we're going to put in our new equation. I'm going to use the variable x in the calculator, okay? But in our problem, it's the variable z. That's okay. It's going to be okay. We're just looking to get a number out of here anyways, and so we're just looking for a numeric answer. Alright, so I need x times e raised to some power. So down here we have the natural log button, and right above it in yellow, we have e to the x. So we're going to second hit this natural log. We want that e. Alright, so we hit second and then hit this natural log button to get the e raised to something. So we have e caret, open parentheses. Alright, we always must remember to close parentheses or else our calculator is going to have a freak out moment. Okay, so then we need this square root, which again is a yellow function here. So second, get the square root. Now we have a second set of open parentheses. We have to remember to close both of them. Then we need z, or x, plus 1. Alright, close the first set of parentheses, close the second set of parentheses, and there we go. Alright, so our window's already set in our typical negative 10 to 10, so we can go ahead and graph it. Okay, and now we need to hit second and calc. I'm going to go ahead and hit number 7. We want that integral down here, so I hit 7. Our lower limit is 2.1, so we want 2.1 as our lower limit. Enter. And our upper limit is 3.5. 3.5. And while you watch it shade it in. And our answer is about 28. Alright. 28.02 if you round up. And here you see me scratching things out. Like I said, this is a little bit behind the scenes. Alright. And lastly, we're going to do part C. Here we have a negative lower bound, which is different. We haven't seen that yet. Okay, but it's nothing crazy. It just means we're going to start over here on the x-axis. Okay? So I'm going to go back to my y values and go ahead and decommission this one. And now I want a new function. So I want this fraction. And again, we have to use some parentheses because fractions can be difficult when putting them into a calculator. I'm going to go ahead and move my calculator back up because I realized we can't see half of the buttons that I'm pushing. Okay, so we need 1 divided by, so this division symbol, I'm going to do open parentheses. We need square root, so second square root, x squared, so x squared, plus 1, close 2 sets of parentheses. Alright, go ahead and graph that. And then we're going to go ahead and calc down to integral. Our lower limit is negative 7. Be careful when you're putting negatives into a calculator. You have to use this negative in the parentheses. You can't use this, which means subtraction. Okay, you'll confuse the calculator. So negative 7 is our lower limit, and 10 is our upper limit. Go ahead and hit enter. It's going to shade in and calculate the area. We just watch the whole thing is shaded in now, and our area is 5.64, which is the correct answer. Alright, so thanks for bearing with me with this new type of video here. Hopefully it wasn't too blurry. Let me know if you have any questions, and I will see you in the next lecture.